Welcome to the next chapter. This is chapter 16, also known as acid-base equilibria. There will be several parts to this chapter. This is part 1. And of course, I'm your favorite teacher, Ms. Bedrosian. The first thing we're going to look at are the strong acids. Obviously, you know them already, I'm sure. But just in case you don't, I'll pretend you know them. Let's just review them really quickly. We have hydrochloric acid, hydrobromic, sulfuric acid, hydroiodic acid, perchloric acid, and nitric acid. Please note that if it's a polyatomic ion acid, there is no hydro in the name. Let's review the definitions for an acid and a base. There are two that we look at. The first one is by Arrhenius. He defined an acid as a hydrogen ion donor, an H+ donor. He defined a base as a hydroxide donor. Remember, that's OH negative. The other way that we define is similar. It is by Bronsted-Lowry. The definition for an acid is the same. It is he calls it a proton donor, which is what a hydrogen ion is, nothing but a proton. But a base is a proton acceptor. That's where the difference is in the definition. And I thought you said the chemical composition for water was H2O. Get it? Oh, maybe not. All right. So what makes something strong or weak? A strong acid or base dissociates completely when you toss it in an aqueous solution. It means it always comes apart. A weak one mostly stays together. Usually we write it as HA aqueous, that's the acid, plus H2O liquid in equilibrium, and it becomes H3O plus aqueous plus A negative aqueous. That H3O plus is the same as an H plus. We write it the same way because in all actuality, it's no such thing as an H plus. It almost always is attached to a water as H3O plus. But for abbreviation, we write it as H+. So strong acids have weak conjugate bases. Weak acids have strong conjugate bases, and they form a partnership. In other words, when the acid, like HA, releases its hydrogen ion, it now looks like A negative. That becomes its conjugate base, because going the other way, it can accept that hydrogen back. The water in this case is functioning as a base. It is going to accept a hydrogen. That's a conjugate base, and its conjugate acid is H3O plus. So you can see the pairs as they have formed. These two are a conjugate pair, and the other two are a conjugate pair. And here's a little cartoon I found. Now, polyprotic acids can dissociate at different strengths. Polyprotic means it has more than one hydrogen it can donate. The example I'm going to give you is sulfuric acid. The first hydrogen comes off, and this is a strong acid. The first hydrogen comes off easily. They almost all come off when you put it in water. So you get H plus HSO4 negative. The second hydrogen, however, is a different story. It does not come off. It is a very, very weak acid. it mostly stays attached, meaning that when you put it in solution, it's mostly still attached. There's a few that come off, but not many. So that is a weak acid. A couple of definitions, just so you know. An oxyacid means a hydrogen is attached directly to an oxygen. And an organic acid, that looks like a zombie hand, doesn't it? The hydrogen is attached to a carboxyl group, COOH. And this is the end of part 1. Welcome to the next chapter.